This video was brought to you by very generous Patreon supporters. So welcome to my video about intuitively understanding entropy. Let me start out with an interesting question. Say I have some warm coffee, but I want it to become even hotter. How come it isn't possible to take a cold cup of water, put it next to the coffee, and then hopefully the coffee will suck out all of the energy of the cold water? This clearly doesn't make any sense, but can you explain why? In this video, I want to solve the puzzle and explain why heat only flows the other way. This is what the second law of thermodynamics hopes to describe. You guessed it, it's called entropy. Let me start out with the definition of entropy as it's given by Boltzmann's constant k times the logarithm of the multiplicity. The equation is defined like this because multiplicity is a big number, so we are scaling it down by taking the logarithm, and we are multiplying by k to get the units right. Entropy only depends on multiplicity. So if you understand multiplicity, you understand entropy. Before moving on with multiplicity, let me talk about order and disorder. Here is a picture of a glass window. Is this window in a higher order state than a window that's shattered? Who is to say what is order and what is disorder? It only makes sense to us humans. If you put together glass molecules completely random, finding the glass window in this shattered state exactly like this is just as probable as finding the window in a complete perfect square. So entropy is not disorder. By the way, I straight up stole this example from IG in Physics. It's an amazing physics YouTube channel. Okay, now let's discover what multiplicity is. Say we look at a gas. It will have some properties as a whole. It will have a temperature, it will have a pressure, and so on. This is the combined bigger properties of the gas, and it's called the macrostates. But if we zoom in microscopically, we will see a lot of molecules. Each molecule with a specific position, specific speed, and specific rotation and energy and so on. Call that the microstate. But let's simplify our model a bit and instead examine some coins. So here we have 3 coins. And they could represent whatever, but let's say each coin is an atom and the state of the coin, either heads or a tail, represent if the atom is on the left side of the system or on the right side of the system, so it represents a position. So either all atoms are on one side, tails, tails, or they are on the other side, heads, or some mix in between. But it matters what particle is on what side, so we get these different combinations. Just to make sure I'm clear, this state represents that particle 1 is on the right, heads, particle 2 is on the right, heads, and particle 3 is on the left side, tails. Like this. Let's define the micro and the macrostate for this specific system. Up here we have one macrostate because we have 2 particles on the right side and only 1 particle on the left side. It doesn't matter what particle is on what side, but the amount of particles matters because that determines the pressure. That is why we have 2 extra macrostates here at the bottom as well. We can see that all the molecules are at one side while there are 0 molecules on the other side. So the pressure would be high at one side and there would be a vacuum on the other side. What about the microstates then? Well, every combination you can make is a microstate. So here all these states are microstates. Now are you ready? Because multiplicity is simply then the number of microstates given a macrostates. So here in this macrostates the multiplicity is 3, here's 3, and here's 1, and here it's 1 as well. I told you multiplicity and entropy is kind of the same thing, so now that we know the multiplicity we can get the entropy from this function. So with a multiplicity of 3, the entropy will be 1.5 times 10 to the power of negative 23 joules per Kelvin. Now entropy tends to increase, and of course so does multiplicity. But why? It's just because it's way more probable. To see why, let's go back to this example of molecules being either on the right or the left side. And let's change the number of particles to 6. It's completely random what side an atom is on. So what state is more probable? I can show you in this simulation. Here an orange ball represents a state. The ball has to choose between left and right 6 times. It does that completely random, just like our other system. We can see on our simulation a pattern occurs. It is more probable that a state will have taken an equal amount of left and rights corresponding to this state here. You can also see it's very improbable for a state only to go one way, like here, only go left. I mean, of course, if you flip a coin 6 times, it will probably not only be tails 6 times. This means in our setup it's more probable for our atoms to be evenly distributed. This so happens to be the state in which the multiplicity and therefore the entropy is highest. Let me go wilder to give you a better intuition. Here's a few more atoms. Also, I'm counting how many are on the left and how many are on the right. I'm also showing you the multiplicity on this. Let's go. We can see, just as with the other example, it's more probable for the coins being evenly distributed. This also happens to be the states on which the entropy or the multiplicity is highest. So we see that the multiplicity will grow and grow and grow, but it's too improbable for the multiplicity to fall again. At least for a significant amount. Let me speed that up for a bit. And notice we're going for a stable, evenly distributed system, and it will stay like that. This is only for the position and not even in 3D. Remember, the microstate governs more parameters. So let's add another to our simulation to finally answer the question. Let's add the speed. Each atom has a microscopic state, the speed. The average of all the speeds corresponds macroscopically to the temperature. Let's for simplicity assume that an atom only can have 6 speeds. 1, 2, 3, 4, 5 or 6. Again, if we look at a system, let's look at 2 atoms. Their speed are more likely to be evenly distributed. It's unlikely that they both will go with full speed or both go with low speed. At any given time, they will most probably be evenly distributed. Why? Because it is the states with the highest multiplicity. You can easily see that here in a macrostate with lowest temperature 1, 1, there's only one combination of that, so the multiplicity is 1. If I map the rest out, you can see the macrostate of a temperature of 7 has 6 combinations. So it's the more probable configuration and it's the configuration with the highest multiplicity. Throw some dice around, you're most likely to get a combination with the highest multiplicity. Now let's come back to the puzzle here and understand why heat only flows one way. I'll represent the same system but in this box model we used before. On the left side we have the hot coffee. The side has some molecules and they have some speeds. Some speeds that are quicker than the speeds on the right, the cold water. The number I'm showing is the temperature. It's the average speeds of all the molecules on one side. Let's see what happens. It will go to a state with higher and higher multiplicity, meaning the particle speed will be evenly spread, because it's the state that has more combinations and therefore more probable. So we see the temperature averages out. I hope you enjoyed this video about entropy. If you want to support me, become my Patreon, sign up for the email newsletter or subscribe. Links are in the description.